I don't want to play with you anymore. Now I want you. Joke aside, a few years ago I wanted to try making PCBs on my own. Not because I needed, but because I wanted. I know there are manufacturers that can easily do this job for me, but my goal was doing it just for the sake of it. I've tried the photoresist technique and UV mask ablation, but it required me too much patience. I wanted the process to be fast and precise. And that does not mean it is cheap. In fact, I will be using a fiber laser. I really hope that in a near future they will become cheaper. But now I can do fast prototyping at home. This video is going to be very technical. I will try to show step by step what I do to make double-sided PCBs at home. And now I can start with the software part. What I'm going to create is just a simple microcontroller PCB which contains an STM32, in reality a GigaDevice32 F1, but they are one-to-one compatible, almost one-to-one compatible. It has 14 LEDs, and these are for two 7-segment displays, a crystal oscillator, other 4 LEDs that are put in a array, some decoupling capacitors, other things. This is not the best solution that we can get according to the datasheet, but this is going to work. It is not meant to be stable, it is just made in order to work and to have the least amount of components. This is the design. I'm not the best designer of PCB, this is not my job in my life, but I placed the traces very close to each other. The same thing is valid for the components, and I'm not crazy. I'm just trying to push this technology at its limits. The seal screen is all overlapped, but don't worry about that, because this technology, I think, can show its real potential for PCB prototyping and fast prototyping, basically. Seal screen is almost useless in this case. You can see there are a lot of vias. Each vias in this case has 0.4 millimeters of diameter and 0.15 millimeters of the internal hole diameter. Some things must be done in order to get this resolution, and to do that we must go in board setup. In net classes we have to place these parameters. You can try to go with even smaller parameters. These are the ones that for me are the most reliable. We can click on constraints, and generally I place these values because these values allow me to shrink all the components and the traces in a smaller amount of space. Just some consideration on the copper layers. The top and the bottom are filled, and the top I generally put 3.3 volts and the bottom GND. You can do whatever you want in this case, but the most important thing is that you have 0.05 millimeters in clearance and minimum width. You can also in this case try smaller values. Generally these are my most reliables. Smaller than these ones, sometimes the copper can't be etched correctly and the resolution of the laser is going to fatigue a lot. Thermal relief gap and thermal spoke width, you can play whatever you want. Now we have to export the files, but before doing that we must place the origin, and I generally place it in the bottom left corner. We can click on fabrication outputs, Gerbers, and we in this case can activate just these ones, which are the front, back and the mask. No seal screen, no paste, no solder mask, no something like this. probably those are going to be in another video. I just want to make a PCB the fastest way with the highest resolution possible. Another thing to check is drill place file origin. It is very important, otherwise we cannot get the right coordinates in flatcam. We can click plot, then we can click generate drill files, and also in this case we must make sure that drill place file origin is checked. Now we are on flatcam. I've set the resolution of 0.01 millimeters, and we can import the files that we have generated before. I have to mention one thing, and that is flatcam is a software made for CNCs, not for galvo lasers, and so we have to tweak some parameters in order to let it work correctly on a galvo laser and not on a CNC. So now we have to click on the masks and plate a through hole and export them as SVG. We have to do the exact same thing for all of these ones. Okay, you obviously must have to export them in your USB stick or in a place where it is easy to find, because you are going to use them directly on your galvo laser. These ones that we have just exported can be deleted, and then we can click on the front copper Gerber, then isolation routing, and we place in tool diameter 0.0001. This allows us to get the highest resolution possible. If you have already used flatcam in another complete way, because you used it on a normal laser or on a CNC, don't worry, this is going to work, I promise. We can click search and add, then generate geometry. We have generated the geometry of the traces, and then we can click geometry editor. Here the traces are a bit more highlighted, and as you can see, we have made just the outsides of the tracks. We have to click on the rectangle and place another rectangle on the internal rectangle. This will sound strange, but it is necessary to let the other program, the laser program, to read it correctly and hatch it very nicely. And it is also used to protect the bottom and the front layer from the connection of the carbonization of the substrate. And I've done the same thing for both sides. And in this case, we can click once the file and export it as DXF in the exact place where you have exported the SVG files. The first thing to do right now is import all the files that we have made with flatcam onto our laser program, which in this case is BSL app, but I think that there are many other programs like Lightburn. In this case, this one is free. And let's do this. Now I will import all the files And then I will try to select all of them and try to put them on the center. As you can see, there are many colors. For each color there are many options, and I will show them very quickly on the screen right here. Then one by one I will select all the files, click on the hatch button, and with these parameters I will hatch. Now I will assign the colors for each file, for each hatched file. Here you can see how fine the traces will be. I will make another rectangle on the outside. This will be used as the outline and as the reference too. The reference is required in order to mirror horizontally the board if you want to make a double-sided PCB. Here I'm mirroring. The first thing to do is select the rectangle, which is our reference, and then with the control the other part which we want to mirror. In this case, the only part that we have to mirror are the back and the soldermask back, which we will see we will not use because there aren't components on the back in this design. Then we can remove all of them. Don't worry, we will recover them later. And that's it. We will see that we will also have to rotate the holes, but right now we have this. Now we can use the laser because we have to place the board. We can use the red light, which obviously must be calibrated on this kind of laser. We try to align it to the best as we can, and then with just some scotch tape we can put it on. We can put it firmly in place. Some of you may be asking, what is this steel plate which is on top of the main plate of the laser? Basically is just a vacuum plate. I built it in the previous video and I'll show you somewhere right here. I don't know. And its purpose is to make a force and everything I want to engrave with the laser, and this will make uniform pressure onto the entire surface. So since the copper clad isn't perfectly uniform, as you can see, it may have some irregularities, and this obviously will reduce a lot the resolution that we can achieve with this kind of technology. And I want the maximum resolution that I can achieve with this kind of laser, so a vacuum plate is almost needed. And this tape right here is just put in order to reduce the leakage. I know it's not the best way to do it, but for me, at least right now, it is working. Now I have to turn on the vacuum, and that is going to be really loud, so I probably unmute the video. And so right now I'm just lasering the holes and the outside. The holes have just 4 passes. Okay, now with some scotch tape we can stick all of the board onto scotch tape, and then we can pull it very fast like this. Now what we have to do is just rotate it in this way and place it in the symmetrical template that we have made. Obviously we will need to rotate also in the software. All what you have seen was made entirely in real time, and there are a lot of holes, and trying to make them with a CNC, I mean, they are so small. They are so small that a drill bit of this diameter would have snapped almost instantly, and the laser just cut super fast and super precisely without breaking any tooling. Now just a little bit of theory. Okay, I just want to tell you one thing. I'm not going to remove the copper directly with the laser, even if I can, and that is for 2 reasons. The first one is that it's too slow. Probably 50 minutes per side. The second one is that it makes carbonization, and it doesn't seem much, but carbonization make parasitic resistance, and that is actually really bad. To make vias, we have to drill holes as we already done with the laser, and first of all we have to understand that the vias are not metallized. So if I want to connect the front to the bottom, well, we have to make some kind of connection, and we can do it manually, But if we have a lot of holes, that is too much labor intensive and time consuming. So in a previous video I've shown you that I can make a super fine layer which is really conductive using a compound of silver nitrate and not palladium chloride, which is too much expensive. And it works, it simply works. But there is one problem, and that is it is also in this case time consuming, and it makes a lot of chemical waste, also using carcinogenic chemicals that are really bad for the environment. But there is one thing: we can take advantage of the fact that the substrate can be carbonized directly with the laser. In fact, when we ablate the copper in order to make the holes, yes, we can destroy the copper, and we can also engrave the internal substrate. But doing that, we are making some carbonization, which chemical is very stable, and it may have, it depends obviously on the diameter of our hole, but it may have a resistance of about 1 kilo ohm, which is much more than enough in order to electroplate it. So after electroplating, we can make a nice layer of copper. This to me is super extraordinary because it is super fast. I don't have to make another step in order to metallize the internal layer, and simply it does not produce any chemical waste. So super nice. I just want to mention one thing. If you remember, I've rotated the board when I've done the holes. There is a reason. Basically, if I start to make a hole in this direction, we can see the laser beam hitting the board. Some of it will be reflected, some of it will be injected into the materials. So light collision, something related to physics that I don't want to talk about. This will slowly engrave the pattern. And since the carbonization is very light absorbent, we can see that there is a super small amount of light re-emitted back. But as soon as we reach the other part, there is the other side of the copper. So light will be emitted back again. It can be emitted in this direction, but it can also be re-emitted on the sides. This will make some carbonization also on the sides, and this is something that I don't want. So the idea in rotating it is just because I want the hole to be done just right here like this, and then I will make the holes again by the other side. This will start to engrave the internal copper, and once it reaches the middle of the substrate, well, the light can pass through everything, and if some light is emitted back, the copper is not, the light is to the re-emitted light is not strong enough to ablate the copper, so it will reflect again, and this basically makes a hole entirely carbonized on the side and without problems on the edges. Now we will have to electroplate our little board, and to do that I'm going to use a power supply which will help me to let flow something like 100 milliamps constantly. It is not strictly necessary a power supply like this one. You just need something that can let flow 100 milliamps to 200 milliamps, and if you want, you can make some kind of a current regulator. I have this one and it works, it simply works. So I'm going to use this one. I'm near a 3D printer because the electroplating buff, in order to get the highest quality possible, must be heated and at the same time must be shaken in order to constantly break the surface tension of the liquid that must pass through the holes, which in this case are very small. Shaking it and heating it can let pass a bit more easily the electroplating buff into the holes. Right here in this tank there is copper foil, 1 millimeter thick, and I've soldered this cable which will be attached to the plus of the power supply. This will work as the anode and our PCB will be the cathode basically. This tank will be then filled with an electroplating bath. And there is still one thing to know, and that is the fact that the cathode must not touch directly the anode, because the current must flow through the electroplating bath and not directly through a conductive track. So I 3D printed these small spacers that can be applied directly to our board in the edges. Without covering the holes, because we want the electroplating bath to get there. Now we can pick a copper wire and make contact with the board like this. Okay, super easy. The copper wire will make an electrical contact because the sides, the edges, are actually conductive because they are heavily carbonized. Normally I'm doing this with gloves. Now I just forgot them, but the idea is that the PCB is submerged. Then if I turn on the power supply, which in this case is set to 100 milliamps, I don't know if you can see it, I can place the plus or the positive to the anode and the negative to the PCB. As you can see, some current is flowing and there is a voltage and not zero, not complete zero. So that means that there is no short circuit, and so all the board is being electroplated. And then I can start This thing seems stupid, but it is not. This is basically the most important thing of the electroplating bath, because without this kind of shaking, the smaller holes simply can't be electroplated. Now I'm doing this process for 20 minutes, then I will rotate the board and I will do the same for other 20 minutes. If you're asking yourself why a 3D printer and not something else, well, a 3D printer is actually very easy to program and it's much safer. I used another thing that I made in this channel, which was basically a PCB etching system, but after a few trials it completely destroyed itself. I wasn't there in the shop. It simply burned and my shop was completely filled with smoke and the white walls were black. Not something that I actually like. Something that is easier to program is much simpler. I don't have too much time to make a complex system like this one, so a 3D printer was much more than enough, at least for me. And it is not my main 3D printer, but it can still be used as a 3D printer. Now with some acetone I will remove the black paint. Now what I have to do is actually fill all the holes with some spray paint or some normal paint. Spray paint dries more quickly. And I'm going to do this because during the chemical etching process the holes must not be in contact with the acid, so spray paint is going to be the solution. I'm pushing with my fingers inside of the holes so that I can make sure that it will enter, and in this situation I can pick some paper and remove the excess of it. Now with some fine sandpaper I can remove the entire excess. I used sandpaper and not acetone or paint remover to remove the excess of paint because it may enter in the holes and ruin the paint that is inside, which is actually chemical resistive. And sandpaper is also useful in order to increase the surface density of the copper so that the chemical resist, which is spray paint, will attach much better. Right now the PCB is covered with a fine layer, almost invisible, of copper microparticles generated by the friction between sandpaper and the copper surface. To remove it, I'm going to use alcohol, and alcohol will work just fine. It will not destroy the internal chemical resist of the holes. Then I can complete and dry the PCB with some compressed air. Now I have to make a fine layer of white spray paint on both sides. And now I can let it dry with a hair dryer, and I've seen better results with a hair dryer other than just letting dry with normal air. So I'm going to do it. Now I can place the PCB exactly where it was. In the PC now you will have to undo all the steps done before. Okay, you can delete the rectangle, the holes, the mask, and the back side. Now we can rotate it like this and put it again on the template. Then I can undo and eliminate the front side. Now that I have all the traces on the chemical resist, I've put a solution of hydrochloric acid and hydrogen peroxide in this little tank, and in this other one there is just water. So I can proceed to the chemical etching. Okay, in this case I had many more problems that I usually have. I don't know why. I think that's because I have a camera recording, but now it seems okay. So with just some acetone I will just remove the copper paint. I applied the solder mask and I'm not the best in doing it. I'm not using any silkscreen or something like this. Sorry, my cat. In fact, you can see that there are some holes. They don't worry me. Now it's time to solder the components. Okay, now I soldered these wires, and I've already programmed the microcontroller, and in this case the program is just going to let blink some LEDs. In particular, this is the 7-segment display for numbers, this is for letters, and this is a simple LED array. I programmed it with with an ST-Link with the SWD protocol, and now I'll turn it on. As you can see, it is somehow working. I mean, it is working. Basically, I think this process was a success, and it took me 2 years to get to this point. And what can I just say is that I hope you really enjoyed this video, and thank you very much for watching.